Okay, these are the publications on which is great. Let me just skip this because it's going to be mentioned later. An outline of my talk is I will talk about basic bosonic systems for which we are trying to develop variational approaches. In particular, there are some issues in the details of how to calculate the superfluid response. And that's what this talk is concerned with. And I'm going to refer a lot to a somewhat controversial paper of Anderson in which it was claimed that the bosonic Hubbard model is always a superfluid. It gives a superfluid response. We're going to analyze this statement. And in the end, I will also talk about the polarization amplitude as a way to calculate superfluid response. A very famous experiment in 2002 by the Bloch group was the first example of the mat insulator superfluid transition in the bosonic Hubbard model. So here on this part of the screen, you see this egg box, which is actually a lattice, a two-dimensional lattice. And in this, in the upper case, the particles are delocalized, and you see that the momentum distribution is actually very sharp, and that's a sign of a kind of Bose-Einstein-like signal. So you see superfluidity, whereas the particles are localized, the momentum distribution is smeared out. The bosonic Hubbard model, which I'm going to talk about, let me just describe the Hamiltonian. It has a kinetic energy or hopping term between sites, and the parameter is J. And it has an on-site interaction, and there the parameter is U. There are, of course, more complex versions of this because you can introduce coupling between and hopping also between not only nearest neighboring, but next nearest neighboring sites and so forth. It's an old model, and the first studies, I mean, the first theoretical studies go back quite a lot. So the mean field studies essentially predicted these Mott lobes. Depending on filling, you have an insulating state associated with each different filling, and you have the superfluid state. And actually, third order expansion or more sophisticated calculations still maintain this picture with some qualitative differences, like the points you see at the end of the Mott lobes. And the statement of Anderson was that the ground state of the Bose-Hubbard model is a supersolid. And what this calculation was based on, I'm going to go into that in a little bit of detail, but first let me talk about how usually the superfluid weight is calculated. So you have, so this was actually done by Pollack and Sepperly, and the idea was that you take, basically you try to mimic the rotating bucket experiment. The rotating bucket experiment is actually, the idea is that you rotate a sample of superfluid and you measure the rotational inertia. And if you, for example, change the temperature, you can see a drop in rotational inertia when you go into a quantum superfluid state. The way Pollack and Sepperly implemented this is actually, you have sort of a spherical shell or a circular shell of two walls in between which you have a superfluid. And if you take the radius of each to a very large number compared to the thickness, then you actually have a straight line system. And instead of rotating, you give the system a velocity. That's what this MB is indicating. And then actually, you can use straightforward linear response theory to analyze the total momentum, and you can actually separate the normal and superfluid components. Now, we are concerned with variational states. And to start with, you get some sort of paradox in the variational states, or a puzzle at least, because a variational energy is always a probability distribution of exact eigenstates. So this EI is an exact eigenstate. And let me just share with you that here I'm using the notation phi. That actually, I changed notation a bit because it's more common in the lattice case. That's actually the momentum shift MD. Okay, now the question is, if you actually follow this prescription, which is in the bottom here, so if you follow this prescription, you would think that you would have to take the second derivative of the ground state energy with respect to phi, which corresponds to the velocity. But actually, this is not really true, because it turns out that in a variational setting, you have to leave the probability distributions of the exact eigenstates unchanged by the fact that you are rotating the system. Now, this is actually, this formula causes quite a bit of difficulty because you wouldn't be doing variational calculation if you had the exact eigenstates. So basically, this is probably something that in most practical cases, this exact eigenstates you don't have access to. So it's not so easy. This is the correct formula, but it's in most cases, or it's very often not implementable. Now, I'm going to talk about Anderson's approach. Okay, so Anderson's introduces what he calls a set of non-orthogonal bosons. So you take, for example, a destruction or a creation operator, which corresponds to site I, and you couple it to its nearest neighbors. So site I plus 1, site I minus 1. And you couple it, of course, you make a J over U coupling, which is common when you, it's a kind of strong coupling expansion. And then you can actually Fourier transform this, and then you consider the effect of a boost on the momentum, and then you calculate the response by, he calculated the response by taking the second derivative of the energy with respect to this momentum boost. Let me actually just say that if you Fourier transform that operator that I listed, you get basically this cosine k here, and you can implement this momentum boost. Or Anderson implements this momentum boost in this cosine function. So actually, he implements it particle by particle. Okay, now what we have studied is the so-called Deri's through a variational wave function, and it has this particular form. So this form, you first of all start with an infinitely coupled wave function, an infinitely interacting wave function, U equals infinity wave function, and you project onto it by the hopping energy. So this T dagger is actually, T hat is actually the hopping energy, and alpha is the variational parameter. Now it turns out that if you expand this propagator, well, you can easily imagine that T hopping goes both ways, left and right. So actually, if you truncate your expansion here, so in this first order term, you are actually doing none other than Anderson's Anderson's non-orthogonal bosons. And sorry, I should of course emphasize that Anderson found a superfluid response based on this procedure. Okay. Now, what we did is we developed a variational Monte Carlo method which can handle this full wave function. In other words, it's not a cutoff at the first order. You can show that the underlying probability distribution is positive definite, so we can apply Monte Carlo. Each quantum particle is going to be represented by 3 coordinates. Okay, so we call it left, center, and right. This is actually, this is because you have a propagator in your system, and it's kind of like a path integral Monte Carlo method. And XL and XR are coordinates which are sampled from the U equals infinity wave function. And XC are the coordinates where which you have to act, most often you would use them to sample the observables that you are interested in. Moreover, actually, our algorithm is such that bosonic exchange moves can be implemented, but you can also turn it off just to see what happens if there's no bosonic exchange in your calculation. Now, this is sort of a caricature of our algorithm. So here we have a lattice. The black sides here are lattice sides. The red sides are particles. Okay, so this is a filled lattice side. This is an unfilled lattice side. And like I said, we have 3 replicas of the system. And each independent lattice is connected by this so-called propagator, this kinetic energy propagator. Alpha is kind of like an effective inverse temperature. You could think of it that way, but it's actually the variational parameter. And the point is that these particles hop around on their respective lattices. So I said C1, C2, that's the center. So for example, the potential energy you would evaluate using the coordinates C1, C2. These particles hop around and they're sampled according to Monte Carlo. And this propagator that I'm showing here, this kinetic energy propagator, is actually defines your sampling distribution, that the acceptance and rejection criterion. Now, one other thing I should say is that the bosonic exchange moves, the way they are implemented, is you have to propose moves in, for example, this particle and this particle is exchanged, and you have to propose that and then decide whether it gets accepted or rejected. So we have a full method to solve the Beresford wave function in the bosonic system. Is it a good method? Well, we think it's a pretty good method because, for example, the phase diagram, it does an extremely good job in reproducing. Okay, so this is actually, here I'm comparing the phase diagram to state-of-the-art calculations, which are quantum Monte Carlo calculations, and we are in nearly perfect agreement. But the thing is that actually might raise a question about this method is that the superfluid weight, just like Anderson, is finite always. So half filling, if the system is half filled, then you expect it to be finite because you have holes in your system and your system can easily be localized. But when you have integer filling, okay, common knowledge is that you don't have a superfluid response for small j over u, and indeed we find, just like Anderson, a finite superfluid response. But this is actually what prompted a further investigation on our part. So I'm going to actually argue that what is missing from this calculation and also the calculation of Anderson is that there is no many-body interference, and that's actually what's missing. So I'm going to write now the non-orthogonal boson basis that Anderson defines. When you implement the phase, it looks like this, okay? And when you form a many-body wave function from this, then actually it turns out that the different phases will have to interfere. And you can, actually, it's a pretty easy step to show that if you calculate an expectation value, any relevant expectation value, then because of the fact that you have a bra wave function on the left and a ket wave function on the right, these phases actually cancel. So either for both of these cases, the phases cancel, and that actually, if this phase cancels, then you have zero superfluid response. In our so actually, I hope this, I can.
So in principle, your time would be already over, but maybe you can use 2-3 minutes to come to an end then.
Okay, thank you. Okay, so yes, I wanted to restate this, that in our Beresford calculation, we have the same the full Beresford is also like this. You have a 5-phase, and if your system is filled, has an integer filling, then the number of left hops and the number of right hops are always the same. So you will have no phase dependence in any observable, so you have a zero superfluid response. We verified this, so this calculation is the Monte Carlo calculation that we did compared to exact diagonalization for half filling, and we get at half filling the superfluid response is actually in pretty good agreement between those two. And while superfluid response does exist at actually more like 0.3, 0.4, exact diagonalization, these are pretty small system sizes. That's the best we can do with exact diagonalization. Okay, let me also say that the other aspect of our study is the so-called polarization amplitude. And this is actually a quantity that's used in the modern theory of polarization, but we're trying to introduce it to study superfluids. And the idea is that for any ground state, you can calculate the position, a phase operator defined like this. And this is actually a kind of characteristic function. In statistics, a characteristic function is where you get your moments or cumulants from. So if you have a probability distribution Px, a moment is a derivative of a characteristic function, whereas a cumulant is a logarithmic derivative of the characteristic function. So it turns out that you can actually use this quantity, which is known as the polarization amplitude, to calculate moments and cumulants. But since you're in a periodic system, you don't have a continuous k variable. You don't have this is not continuous. You have a discrete k variable. Actually, I denoted as 2pq over L, and you take finite difference derivatives, and that's how you define, for example, a variance. And based on these calculations, so here are the variances. what happens is the following. So this is actually an exact diagonalization calculation in which you see that the variance increases as the hopping increases. That of course makes sense, but the important thing here to realize is that as the variance increases, the size scaling exponent of the variance with system size becomes 2. And 2 is actually, for the variance, size scaling exponent 2, on robust grounds you can expect that that is a superfluid phase. So indeed, even for very small system sizes, this quite accurately reproduces the metal insulator transition. On the other hand, for the Beresford wave function, which I mentioned, which is not supposed to be superfluid at all, you never find that this exponent goes to 2, and you never find a superfluid response. Okay, since I'm at the end of my talk, I'll just conclude. So basically, we constructed the proper method to calculate localization quantities and superfluid weights in this variational Monte Carlo, in actually a general variational setting. And well, we also believe that the Beresford wave function is in the end qualitatively a good description of the system as far as the phase diagram is concerned. And we can also calculate quantities like this from the polarization amplitude. Thank you very much for your attention.